talking about what we learned in commissioning with the chronographs. So brief overview, the chronographs are part of the same detector, or in front of the same detector as the imager. And this is sort of a superimposed image of some simulated PSFs in the chronographs. Here's the annotated version, where the LEO 23 microns is the topmost chronograph. Then we have the 3-4 quadrant phase masks below, and they're in descending order of wavelength. So the 15 micron is the second from the top, then the 11.4 micron, and then the 1065. And then on the left-hand side, these are the keywords that you might find in the FITS headers if you're trying to identify which chronograph the particular file is coming from. And so I've also annotated the LRS and the imagers, so you're sort of oriented based on the previous presentations where these are on the detector. On the right, we have the filter profiles. So the LEO filter is very broad, and it's because the LEO is not sensitive to wavelength, but the 4-quadrant phase masks are very sensitive to wavelength, and therefore their filters are fairly narrow. This is slides from the contrast, the contrast performance that we measured in commissioning, and the discussion of the commissioning performance is available in Anthony Buccioletti's paper. That's linked at the end of the slide. Basically, we get to better than 10 to the minus 4, sometimes almost 10 to the minus 5 contrast in all the chronographs by about half an arc second. The 1550 contrast looks funny because of an issue that I will discuss later. Basically, there was a large wavefront error anomaly that happened during commissioning, and we had to figure out how to adjust for that when we were doing the PSF subtraction. Let's see, but the ERS paper got some very nice results. So these are some slides from the ERS paper. They looked at HIP 65426, which is a 2 solar mass A star. It's about 100 parsecs away, and it has a known companion, 7 Jupiter masses, less than an arc second away. And we got some really nice detections, both in NIRCam, which are the first 5 images, and then in MIRI as well, which are the bottom 2 that are outlined in orange with the 1140C and the 1550C labels. That's the filter label. Even though it's 0.8 arc seconds, we have a relatively large pixel scale, 110 milliarc seconds per pixel. So even though it's pretty close to the chronograph, we got a really nice detections of this companion. These are the contrast curves from the ERS paper, which are a little higher than what we measured in commissioning. That's because of their particular exposure parameters and the backgrounds. That's their particular configuration. But basically, you can expect to get 10 to the minus 4 contrast for your observations. And you can always, the ERS paper is really great. They have a really great discussion of their methodology, and that's going to come up a lot in my slides. We've been working closely with their team to come up with best practices and recommendations for the community. So the ERS paper is a great resource. Oh, and that has a reference in the bottom corner, but the text is white, so you can't see it. I'll fix that in the slides. So a lot of the recommendations that we are going to give you are driven by the Glowstick anomaly. This is what your data looks like when it comes down from the telescope. There's a big, fat, bright stick across the middle of the detector, the chronographs. It follows the boundaries of the 4-quadrant phase mask, and it's also along the edges of the LEO detector. And it's sort of, we believe it comes from stray light from the observatory. We think that there's a path that comes from the structure, the sun shield structure, that makes it all the way to the chronographs and illuminates the detector. And so the way to deal with it, it really makes data processing challenging. So we now require dedicated background images to remove them. But the dedicated backgrounds work really well. So this is a recent calibration program that we took. The top is before subtraction, and the bottom is after subtraction with your dedicated backgrounds. And love, especially the Leo, it looks really nice. And also the benefit of the background observations is that it remove a lot of artifacts, like hot pixels, from your images. Anyway, I think the point of this is when you're preparing your program, just like the MRS, you will need to take some time, dedicate some time to backgrounds, but also don't be shocked when your data come down and you can't really see anything. You have to take the time to subtract the backgrounds before you can you can assess their quality. When you take a background, we highly recommend you dither. There's a little switch. I've taken a screenshot from APT with an arrow pointing to where you put your dither, where you select a dither. So this is an example from this recent calibration program. There was a point source in one of my dithers, and then when you combined it, the point source is removed. The exposure time, just like how Kirsten said with the MRS, it should match the time of your science exposure. The recommendations to the GTO programs, since it's guaranteed time, and we've been experimenting with our background subtraction optimization, we've been having them have both dithers be equal to, each dither is the same length as the science exposure with the same parameters, so the n groups, number of integrations, number of exposures. We're not sure that that's necessary, and some of them have been able to get a good background with just one of the dithers, so you might not need to be that aggressive with your background subtraction. However, but back to why dithering is important. Web is very sensitive. This was my screenshot from Aladdin from my APT file for this calibration program, and I tried really hard to pick a background that was source free. There was a source of it anyway, so we highly recommend you dither, even though some of the GTO programs have gotten away without dithering. For target acquisition, our initial plan was to offer 4 quadrants. So you can see in the grayed out areas, this is a zoom in of the Leo region, of the Leo chronograph with the target acquisition regions emphasized, annotated. So there's the 1 in the upper right, 2 in the upper left, 3 in the bottom left, 4 in the bottom right. And the initial impetus for offering 4 regions where you can do target acquisition is for latent image mitigation, so that you could repeat your observation with T in a different quadrant, and then your unocculted star would be in a different area, and you could make sure that you weren't accidentally detecting a latent image, a residual from your primary when you were looking for planets around your brand new around your disk. During commissioning, we found that for unocculted sources, latents really are not a problem, and none of the programs that have executed so far have had any issues with their latents. And because of the Glowsticks, we were unable to commission more than the first quadrant in time. So we're working on getting the rest of the quadrants. We're basically doing them as needed. Right now, we can only use the neutral density filter, even though there are 3 other filters available for TA, hopefully in the future. If you have a program already, you might have received an email from us asking you to change your TA to only quadrant 1. And that's worked for everybody so far. This is sort of a 90% use case of a bright star that needs a neutral density filter anyway, in quadrant 1. So be aware that we only have quadrant 1 and neutral density filter available for TA at the moment, but more will be added as needed. So don't worry about, when you're making your science case, your initial proposal, don't worry about the TA quadrants. We'll work with you to take care of that for the phase 2. All right. So those are the major recommendations that are new since commissioning. The summary of the best practices is here, and this is, for your reference later. The pipeline provides well-calibrated individual data products, the best strategies for the backgrounds and combining your reference PSFs with your target PSFs for PSF subtraction are still under development. So our recommendation is to take the individual data practices, individual data products, combine your, produce your own backgrounds, do your own background subtraction, and do your own PSF subtraction as well. We have some notebooks that will guide you through it. We recommend the ERS paper. They have a really great discussion of their data processing. And they also produced, part of the deal with the ERS was that they would produce a pipeline, software for the community, and it's really nice. It's called SpaceClip. The link is here. And so it's not only well developed to do PSF subtraction, but it also has extra utilities to reprocess data through the pipeline, make your backgrounds, sort of touches that they've made for optimizing chronographic PSF subtraction and data processing. For astrometry, so since we recommend you do your own processing of basically the cal files, the cal-ins files, they are not corrected for distortion. So you have to be aware of that if you're trying to measure your relative astrometry, that they're not corrected for distortion. The distortion model is available in the FITS headers. And here's a snippet of code that you can use to map your pixels to RA and DEC. And even if the WCS information, there are some uncertainties associated with it in the absolute pointing, but the relative astrometry that error should come out when you're measuring your relative astrometry. But anyway, but also the distortion is small, and you'll be dominated probably anyway by the uncertainty in the pointing, which is about 10 milliarcseconds. Last thing, which is the problem we had in commissioning with the contrast curves, if your PSF subtraction just isn't working and it's not because of glow sticks, you could check the OPD maps, because we are very, very sensitive to the wavefront. So for example, this is the OPD maps. These are the OPD maps. This is the wavefront maps for the calibration program. This is one wavefront map before and one wavefront after. Differences are very small. This is what happened during commissioning in between when we were taking our target and reference slides. There was a micrometeorite that hit one of the panels, and they had to rephase the mirror to get the wavefront error back under control. And we were unable to, even after the rephasing, we couldn't use the target files, which had which were taken under one wavefront error map, and the reference files, which were exposures, taken under different. They were not able to subtract each other. So the subtraction was not good. So you have to have consistent wavefront error maps. If the total wavefront error is worse or better, it doesn't matter. What matters most is that they're the same. So if you're really having trouble, you can always check the wavefront maps, and WebPSF can get them for you. This is a list of resources for you to refer to.